So this is a short introduction to integration theory. Now, in most subjects, I tend to just dive in and start giving definitions and examples and calculations and so on. But in this case, I think a little bit of a preamble is really necessary. So we all basically know what an integral is, right? If I draw this function f here, this black curve, then we know the integral of f from 0 here to 1 here is just, well, look at that green stripy region and compute its area, right? That's the integral. That's more or less how we all learned what integrals were. And that's right as far as it goes, right? That really is what I mean by an integral for that particular function. But if you sort of jump ahead into the videos or into the lecture notes, you'll see that integration theory, well, doesn't look a whole lot like that. We're certainly not talking about areas a whole lot. And I think it's easy to come away with one of two impressions. One is that all of this sort of fancy version of integration theory isn't really necessary because we all know what integrals are. And the other sort of opposite possible impression you can get is that in order to define integrals at all, you have to do all of this sort of fancy technical stuff. Otherwise, you don't really have a rigorous definition. And neither of those things are really true. So we're only going to give one real integration theory in this class, but I sort of want to point out, if you look in other analysis books, there are actually a whole lot of integration theories, which range from fairly simple ones, which only work some of the time, to really, really sophisticated ones, which work in much, much greater generality. And it's sort of unfortunately the case that all of those are sort of useful tools to have in your toolbox. So before I get into the most technical definition, I'm going to say a little bit about why this sort of simplest possible definition doesn't always work, and give an integration theory that's a little bit simpler than the one that's in the lecture notes, but somehow not quite as simple as just looking at the area. Okay, so that's sort of the goal right now. So first of all, there's a sort of a question, right? Why can't we just use the area for everything? And the short answer to that is, yeah, this is a really good theory when you know what the area is, and in particular when you can draw the function f. But as we know, there are a whole lot of functions that you can't really easily draw. So there's sort of a canonical one that's easy to write down, where sort of the problem is obvious. I can define f sub x to be 1 for all points x which are rational numbers, and 0 otherwise. And so if we try to apply this sort of naive theory, well, we sort of have to plot f, and what does f look like? Well, we have a lot of ones. We have ones at every point in Q, so sort of all of them up there. And we have zeros, sort of every point that's not in the Q. And we know that the rationals, in fact, are dense. So if you were really to sort of draw all of these dots in and then put it into my finite resolution monitor, you actually just have a line up here, which is really the function. But you also have this line down here, which is really the function. And they're both sort of everywhere. And who knows what the area of that region is, right? It looks really weird. So this sort of naive definition clearly isn't going to be good enough. Now, you might be looking at that and going, well, all right, in this particular situation, it's sort of obvious, right? There are many, many fewer points in Q than there are outside of Q. But turning that into a careful definition, I hope you can sort of immediately see you're going to have to do a little bit of work to sort of test that intuition, or to figure out what this integral is supposed to be. And unfortunately, this isn't something that we can just sort of sweep under the rug. So it turns out that there are some areas of math, so I'm a probabilist, certainly in a lot of probability theory, where we really want to integrate a whole lot of functions f that are weird looking, sometimes even weirder looking than this function here. So you actually need that to do a lot of mathematics. And it's an unfortunate fact, and this we're not going to get into this course, but you can look this up, or I can give you details later, that actually it's not possible to cover every function f in a coherent theory of integration that sort of does this, that looks a whole lot like our naive notion of area. So that's highly non-obvious, but unfortunately it's basically a theorem. Okay. So as a result, we spend a lot of time trying to come up with notions of the integral that are sort of as generic as possible, but they can't be all the way generic because there are actually limits there, which are sort of good enough to do all the different types of math that we do. Okay. So we're going to give some version of integration called the Riemann integral in this course. It's not the usual version of integration that mathematicians use, but it's a lot more careful than the naive version that you probably saw in calculus class. And in this video, I'm just going to give a really short sort of intermediate version of the integral, which is pretty easy and is good enough for a whole lot of functions that you might be interested in. Okay, so this is easier than the theory we're going to cover in the rest of the class, and it's good enough for most purposes. So here's a picture. It's nice to talk about integration when looking at pictures. I'm going to start talking about integrals for generic continuous functions f on bounded intervals. And we know that continuous functions on bounded intervals, in fact, are uniformly continuous, right? We saw that quite a long time ago in the course. So I'm going to draw one of those functions, and it sort of looks like this black curve bouncing up and down. And I'm going to define two approximations to this integral. And I'm going to define approximations for every integer n as follows. There's going to be the lower approximation ln of f. And what is the lower approximation ln of f? It's the area of these blue rectangles. And where do these blue rectangles come from? Well, I'm going to divide the interval from a to b into exactly n even pieces. So the first point in the interval is a, and then this point down here is a plus 1 over n times b minus a. Okay? And then similarly, all these points here. So I split the interval into n evenly spaced pieces, and then the top of this blue curve is just the lowest value that f takes on that interval, in this case from a to a plus 1 over n times b minus a. Now we know that f is continuous and it's on a compact region, so actually there really is a point here which achieves that minimum, and so that's sort of what that is. Okay, so that's my lower function. That is to say it again, I split the interval into n even pieces, and I draw a rectangle in each one of these pieces with height given by the lowest point that the function takes in that region. Now, whatever you think the area under the curve f should be, it's clear that this blue curve that I've drawn is below f at every point, so definitely the area under that blue curve had better be less than the area under the black curve, right? The blue curve is pointwise beneath the black curve, so definitely the area is going to be smaller. And this green curve, this upper curve, is exactly the same idea, except instead of taking the smallest point in every region, I take the biggest point in every region. So my green curve now is above the function f at every single point, and so definitely whatever the area under the black curve is, it had better be less than the area under the green curve, right? Now again, I haven't defined the integral of f yet, but just sort of looking at the picture, it's clear, right? There's more stuff under the green curve than there is under the black curve for any sensible definition. Okay, so those are the green curves and the blue curves. Now let's turn this into some mathematics. And to do that, I need to make two observations. The first of these is this nesting property. So I've written down a whole lot of inequalities here, but I'm just going to focus on a couple of them. The first one is that L sub n is less than or equal to L sub 2n. In other words, when I have twice as many points in my approximation, then the lower bound is going to get bigger. And why is that true? Well, I have, again, a picture proof, which is as follows. If I look at one part of the curve, say I'm looking at L1 and L2, when a is 0 and b is 1, and I have this sort of black curve here. What's L1? Well, L1, the height of L1, is this green line here, which is the lowest value that f takes between 0 and 1. If I look at L2, then what happens there? Well, the height of the blue curve from 0 to 0.5 is the same as the green curve. It's this here. It's this point here. But from 0.5 to 1, it gets a little bit bigger. It's the smallest value of f which occurs between 0.5 and 1. And if you look at the definition, I'm looking at infimums here. The smaller these intervals get, the bigger the infimum gets. That's really a theorem, right? If I take an infimum over fewer values of x, that infimum is going to get larger. And that's exactly what goes on here. When I have twice as many parts of the interval, then my blue curve, which is here, dot, 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 and then going up, is above my green curve at every point. And then certainly that means that the region underneath the blue curve is bigger than the region underneath the green curve. And that's this first inequality. Exactly the same idea gets me this inequality over here, except in this case, I'm looking at approximating the curve from above. So as my regions get smaller, the approximation from above goes down. For the same reason, the approximation from below goes up. Okay, so that's where those two inequalities on the side go. And then I have sort of a missing inequality in the middle, that all of the L's are less than all of the U's. Why is that true? Where all of the L curves, all of these lower approximations, are below f everywhere, and all of the upper ones are above f everywhere. So definitely that means all of the upper ones are above all of the lower ones. Okay, So that's where that's coming from. So again, this is just a picture proof, but it's not terribly difficult to make all of that rigorous. It's not in the lecture notes. We're not going to examine you on it. So I'm just going to sort of skip ahead for now and keep this informal introduction to integration theory. The next part to look at is to take advantage of the fact that f is continuous, and in particular, it's uniformly continuous. So if I look at one of these little chunks here, that is, if I look at the distant difference between the green curve in one particular region and the blue curve in the same region, that difference is going to go to 0. Why is that true? Well, I'm looking at the supremum of f over some interval minus the infimum of f over that interval. And as we know, as the length of that interval, which is 1 over n, goes to 0, we know that the difference between the supremum and the infimum goes to 0 as well. That's really what it means to be uniformly continuous. Okay? So I'm not going to go over this except to say you can trust me on this. I'm just unpacking the definition of uniform continuity when I make this particular claim. Okay? That's true for every single interval, and since un is an average of such of the greens and ln is an average of the blues, if every single one of the differences is less than epsilon, then certainly the average is also less than epsilon, right? If all of the numbers are in a list are less than epsilon, then of course the average of the numbers of lists must also be less than epsilon. So if I combine these two facts, what have I shown? I've shown that ln is less than L2n ... So the ln's are getting bigger. And in particular, that means by the monotone convergence theorem, they have a limit as long as they're bounded, which they are. And the UNs are going down, and that means, again, by the monotone convergence theorem, that they have a limit. So that is, L2 to the nf is converging upwards to some number L. U2 to the nf is converging downwards to some limit, which I'll call U. And then by double star, the difference, U minus L, has to be less than epsilon for every epsilon greater than 0. So that means actually they have to be really the same. So what am I going to do? I'm going to do the obvious thing. I'm going to find the integral of f from a to b to just be this common limiting value, L or U. Okay. So that was a very informal introduction to integration theory. But I will tell you, there are really only two claims I made, the star and double star. And both of these really, I swear, you can unpack them pretty quickly and turn these into real theorem statements. Okay, so I didn't go over the proof because we're going to be going over a sort of more precise integration theory in a moment. But this is really a precise integration theory. It's an easier integration theory than we're going to do in the rest of the course. And it's fine. If all that you care about is continuous functions, which is a perfectly reasonable thing to care about, this really gives you integration theory, right? It really gives you a very sensible theory which covers all of those. The only reason that we keep on going is that actually sometimes we care about non-continuous functions. And for those particular functions, we could easily have L not equal to U, in which case this definition up here wouldn't make any sense. So to give one of the examples, to go back to the simple indicator function example we had before, if f of x is 1 on the rationals and 0 off the rationals, then it's very straightforward to check that L is 0 and U is 1, and so who knows what this integral should be. Okay, so that's the reason why we're not stopping here. So this integration theory isn't as general as we'd like. It doesn't answer every question, but it answers certainly a reasonably large number of questions, and it's a nice, simple theory of integration to keep in mind. In the next couple of videos, we'll do a little bit better in this course. And as a small advertisement, if you're interested in this stuff, there's a subsequent course on the subject called measure theory, which is going to do a whole lot better and introduce sort of the modern notion of integration. Okay, thanks very much. We're going to be getting into more integrals next video.